Therefore, I wanted to give you some introduction to the terms, terminology, and basically this lecture is going to share about statistical analysis, okay, but really just the principles, okay, principles and basic understanding of statistical analysis. All right. Okay, so the learning objectives today to describe the types of data, which will help you determine whether to use parametric or non-parametric tests. Okay, and then we are going to summarize continuous and categorical data into graphical illustration, descriptive statistics. Okay. And thirdly, you are going to understand a little bit about using inferential statistics. So the key words here, you must know the type of data that you have. When I say type, it means whether it is normally distributed or not normal, whether your data is continuous or categorical. And based on these two, you are going to decide whether to use parametric or non-parametric tests. And subsequently, whether you are going to use the type of inferential and descriptive statistics that you can use. So the type of data will help you determine whether to use parametric, which is for normal data, or non-parametric, which is non-normally distributed data. So for each of these types of statistics, parametric or non-parametric, you have different statistical tests that you need to use, which is why it is very important, the underlying principle of knowing which type of data that you have. Secondly, you want to know whether your data is categorical or continuous data. We will speak a bit more about them, and I will be giving you examples. So these data, categorical or continuous, can be summarized in the form of graphics or also using descriptive and inferential statistics. Thirdly, you want to know whether your data consists of dependent variables or independent variables. If everyone could kindly mute your mic, that would be helpful for everybody. All right, dependent or independent variables and the number of groups that you have will help you also to determine the type of inferential statistics that you are going to use. So I think from these terminologies, you can already guess that descriptive is simpler than inferential statistics. All right, and you are going to understand a bit more in the next few slides. So as we said earlier, types of data, okay? You have continuous, which means numerical numbers. Continuous data, you always have numbers which are continuous. That means you can't put a full stop or you can't separate the numbers. Examples of these would be height, weight, BP, age. To give you a better understanding, height, for example, when we say it's continuous, one person can be 160.5 centimeters tall. Another person can be 160.8. Another one, 161 cm. So if you arrange, for example, your class, all of you, in a straight line, and we take your height, we can actually arrange them in such a way that you are so close to each other, we cannot categorize them, okay? Of course, we can categorize 160 cm to 170 cm students, you will be in one group. 170 cm students to 180 cm students, Okay, this we expect more boys in this group. You can categorize them into category 2. But when we say continuous, it means your data is arranged continuously. Okay, so your height in 160.3, 160.4. Okay, so this is what we mean by continuous data, data which can be arranged in a continuous format. Now, categorical are not numerical data, which means they have names to the categories. Examples would be, are you a non-smoker, a smoker, or ex-smoker? All right. Are you having blood group A, O? Okay. What is your blood group? So these groups often have names attached to them. Categorical data can be further divided into nominal, ordinal. So the example just now for blood type, as well as whether you are a smoker or not, are examples of nominal data. Ordinal data is when you can arrange them in order, therefore ordinal. For example, heart disease. Is the staging of your heart disease, is it mild, moderate, or severe? Next, I wanted to give you an overview of the statistical test. So your data can be categorized into categorical data, which are divided into nominal or ordinal, or continuous data, which are numerical in numbers. So once you have an idea of what type of data you have, you can then decide for descriptive statistics. For categorical data here, you see that you can present your data in terms of frequency or percentage. Okay, for example, just now, how many of you, how many here refers to numbers? So that is frequency. How many of you belong to the category 2 of 170 cm tall to 180 cm of height? When we say percentage, what is the percentage of you? Or what is the percentage of the males in your class who belong to category 2, where they are 170 to 180 centimeter tall? For continuous data, you remember your data, your values are all continuous, which means they are arranged from, of course, not zero, but probably a minimum of, for example, 150 cm to perhaps there are few of you who are 6 foot, all right? So that would be your maximum. And in between, you have your decimals, your points, okay, in the form of continuous data. So what here, how you would describe your data is whether you would use mean. Mean is when your data is normally distributed. I hope you have some understanding about bell-shaped graph, which means if I were to arrange all your height in order, that means from the least tall to those of maximum height, I would get a bell shape, which means most of you will be towards the center, will be focused towards the center. But there will be some outliers where some of you will either be on the extreme end of what do we say, vertically challenged, or crudely we say short, or on the extreme end of being very tall, 6 foot and above. But otherwise, the majority of you would lie in the center. So if I were to arrange all your height and plot a graph, I would get a bell-shaped graph. And the middle point is mean. When your data is not normally distributed, that means I do not get a bell shape. If I get skewed data, which means instead of a bell shape, I get a graph where it is pointing more towards the right, for example. That means too many of you are tall. So I am not able to get anyone short to balance the curve. You will see some examples of graphs later on, but just to give you an understanding, median, therefore, will be used for non-normally distributed data. If your shape of the graph is not bell-shaped, okay? If not equally distributed on both sides, you are going to use median to describe your data, okay? Now, other measures that you will use to describe your data, again, these are descriptive ways of describing your data. So here you have described your type of data in terms of frequency, percentage, your central tendency. How close are your data towards the middle? And then you have measure of variation, which can be described using standard deviation range from the medium to the maximum. And then you have IQR, which is your interquartile range. The other way of describing your data is using graphs. For graphs, for categorical data, you remember categorical means you have names attached to them or the order. So you can put them in bar chart. So like just now, category 1, we have 160 cm to 170 cm of height. 170 to 180 will be category 2. Similarly, you have also clustered bar chart. It's just a more two categorical variables available in that graph. Okay? So you have two variables instead of just height. So you may have height and weight in one. Okay.
She was talking. What to do?
Okay, sweetie. I'll get back to you, Danik. I'm just talking to, giving a lecture. Okay, that was categorical data. For continuous data, you can use histogram. Okay, histogram is similar to a bar chart.
Except that bar charts can be for discrete values while histogram for non-discrete values. Next, you have box and whiskers plots, which may have lines extending from the boxes to indicate the variability outside the upper and lower quartiles. Following that, you have the dot plot. It's called a dot plot, a dot chart, or strip plot. Okay, so relatively small numbers in a type of histogram-like chart. All right.
Scatter plot are two ways. So you have your x-axis and your y-axis. Two continuous variables will be plotted against each other. So for example, just now, the height and weight. We could see whether the taller you are, the heavier are you. So what we can do, we can plot height on x-axis and y, you can plot weight. Okay, and when you plot the graph, you have dots in between, and then you're going to draw a line across these dots to see whether you have a linear correlation. So the question is whether when the height increases, does your weight also increase? Remember, I had told you that you had a few ways of determining what your data is. So number one, it was to see whether your data is categorical or continuous. We have done that. The next is to see whether your data is independent or non-independent. So when we say data, you can also call it variable. Okay. So variable, for example, in the earlier example, height is a variable, weight is a variable. Okay. So when we say independent data here, it refers to unpaired data, which means there is only a single observation for each subject. So what this means is it is useful for research where, for example, I want to see how tall you can jump. So if we ask about 10 of you to line up in front and just get the 10 of you to jump as high as you can, and there is someone who's going to observe or sort of measure how high you can jump. That is single observation. When we say non-independent or paired data, it means there are repeated observations for each subject. So here we have to bring in time. When time equals to 0 seconds, the 10 of you are going to jump. After that, we probably will get 5 of you to rest, sit on the chair and rest, another 5 to maybe climb up the stairs and come down. After about 5 minutes, when t equals to 5 minutes, so 60 times 5, that would be 300 seconds. Remember earlier it was t equals to 0 seconds, now t equals to 300 seconds. At the point where t equals to 300 seconds, we are going to get all 10 of you again to jump. And then we are going to see whether there's a difference, excuse me, whether there is a difference in the height that you can jump. So remember, 5 of you had your rest, while the other 5 were going up and down the staircase. So we expect that those who had been given a rest to jump higher than those who had to climb up and down the flight of stairs. So here measurements are taken before and after. All right, but for the same subject. So this is what it means by paired data. So here non-independent also refers to dependent. Dependent means in Malay we will say bergantung kepada satu sama lain. Okay, dependent. Independent here it means unpaired or tidak bergantung. Okay, so it is just a single observation. Okay, you have now learned how to describe your data descriptively. Okay? You remember that extensive sort of mind map that you had seen earlier. So you had descriptive, you had graphical illustration. Okay, so descriptive, how you're going to describe your data when it is continuous and when it is categorical. Okay, so that basically refers to number 1. Descriptive analysis is used to describe the data set. Okay, it's simply a very simple way of just describing it. Describe means what you can see is what you describe. Here, inferential refers to conclusions that you want to make about a population. Okay, a sample is basically a subpopulation. You are just using a small sample in order to make conclusions about the larger population. Population here refers to perhaps Malaysian population. If you want to take the example that we used earlier, you yourself as a class is a sample that represents the youth of Malaysia. So the youth of Malaysia is population, and your class is a sample. We are going to use your sample, data that we gather from you as a sample, and try to generate conclusions to say that when we arrange, for example, the use of Malaysia, okay, if we are going to arrange every single use of Malaysia in a straight line and we take their height, we are going to get a bell-shaped graph, just as what we got in our sample, which is a sample of 158 students. Okay, so inferential statistics, as you have come to know now, is a bit more complicated than your descriptive analysis. Okay. Okay, at this point, I would like you to click. Okay, I'm going to just put it on your screen. Just a second. I have shared the Mentimeter link. Okay, I would like, do you see anything on your screen right now? Great, let me go down. Anything at all? Anyone has already tried it? All right, great. So 3 answers, a maximum of 3 answers. Okay, are you able to see what I see? That 45, okay, it's about 50% of you, half of you agree that you need to decide based on whether your data is normally distributed or not. That would help you decide whether to use parametric or non-parametric tests. So, all right, I think most of you have already given your answers. So the answer to choose between reporting a mean or median is correct, because for mean, it is suitable only for data which is normally distributed, meaning it has a bell-shaped curve. Secondly, to decide whether to use parametric or non-parametric tests, absolutely, that is the absolute number one reason why we want to know whether your data is normally distributed or not.
And whether to use descriptive or inferential statistics, that statement is false, yeah, because both normal and non-normal data can be described using both descriptive and inferential stats. So the third statement is false.
Thank you to all of you for your participation. All right, so there you go. You have your statistics over there in the form of a bar chart. But here, you see, if I were to plot this graph, will I get a bell shape or not? Yes or no? I wouldn't. Yes, I would not get a bell shape, okay? Because the graph is actually skewed to the left. All right, now we have come to inferential statistics, okay? I really just want you to understand for inferential statistics, meaning in order to make a conclusion based on your sample, to make a conclusion for the overall population, larger population, if you will, meaning a sample is a very, very small subsection of a population, and you're going to use that to inference a larger population. You have 2 tests that you can use. Number 1 is correlation. Correlation will give you simply the magnitude and the strength of two variables. Here, which is your first variable? Can one of you type out for me looking at this graph here? Blood pressure reading versus stress test score. Can you name me one variable that you see on this graph? Stress test score is one variable, which is on the x-axis. What is the other variable which is on the y-axis? Yes, absolutely, blood pressure reading. Here we want to look at the correlation. Correlation, you can also call it relationship between two variables. Yes, got it right, Ayman, Mohammed, Hamizan, all of you have got it right. The correlation between blood pressure and stress test score, we want to see whether there is a positive correlation. So when we say positive, the line here is going from small to high. So you can see when someone's blood pressure is, let's say, 65 at this point, the stress test score is 50. When someone's BP is 65.5, here, the first red dot, the stress test score is increasing 53. Okay, and next you have a BP of lower, so probably we call this 65, all right? 65 and your stress test score is 58. So you go on to plot for your sample. Okay? You remember you have a small sample of probably about 50 of you. So you go on to plot for every individual, for every sample, for every subject. They here, you notice they all mean the same: subject, sample. Okay. And when after you have plot, you want to draw a straight line as across as many dots as possible, or to keep it in the middle as much as possible in the middle. Okay, this is to ensure that you take into account all your data here. If you were to plot it, for example, here lower, what about this? The ones that are at the top, the ones that are at the bottom. Okay. Of course, you have a few outliers. Outliers means data which does not conform to what the others are pointing towards. Okay, so you will have some outliers such as this one, this person. Okay, you will have a few which you cannot take into account. However, the majority will be taken into account if you join the dots in the middle or as center as possible, like is shown here. So here we can see that there is a positive correlation. And what about the strength? So remember, for correlation test, you can describe strength and magnitude. So magnitude means whether it is going in a positive. The strength here means the sort of intensity. That means I'm going to describe that a bit more, okay? But strength and magnitude is what correlation test can describe. Magnitude here refers to whether it is positive or negative. So in this case, this is positive because with every increment of perhaps a value of maybe 1 test score, you get an increment of 2 mmHg. You remember blood pressure is measured in mmHg. Okay. So with every increment of 1 test score, you get an increment of 2 mmHg of BP. And therefore, you have a plot which is positive. To give you an example of negative magnitude is if the line is going this way. Oops. Can you see here? If it was going this way, opposite, negative. That means with every increase of the stress test score, your BP also going down. Okay? So that will be negative. This way is negative and this way is positive. Okay? So firstly, the magnitude, and secondly, the strength. So just now, the strength is when I describe with every increase of 1 stress test score, your BP increases by 2 mmHg. So that is the strength. Okay. Regression is what you have here, this equation. Okay. Here, what it means that it is not, okay, regression is usually a bit more complicated than just this very simple equation. Here you have y, stress test score equals to 42.3 plus 0.49 times your BP score. Okay, so this, how you remember correlation and regression analysis forms inferential statistics. So you want to make conclusion for your population. So here what they're saying is you can take anyone based on your sample here of 50 people. You can sample anyone in the larger population. You can just approach an uncle on the street, get his BP reading, his stress test score, and you can predict what his BP reading is. So why? Remember his BP reading, okay, Uncle A, we don't know what his BP reading is, but he has his stress test score. So you invite him, get his stress test score, you use his equation which you had got from your sample, you plot 42.3, not even plot, you just use your calculator, 42.3 plus, you times his stress test score, times it by 0.49, and you get his BP reading. Okay, so this is what it means. Regression can give you a conclusion about the wider population. All right. So I really want to just highlight to you why inferential statistics, how and why it is different from descriptive. Okay, you remember your descriptive, you simply can just describe your mean, okay, median, okay? That's it. All right. So I am going to show you some reading material here. Are you able to see this? Yes. Okay, great. Can perhaps one of you just offer or volunteer to just read one paragraph, the first paragraph, regression and correlation analysis. Can you just read that for us? Unmute your mic and just read.
Regression analysis involves identifying the relationship between a dependent variable and one or more independent variables. A model of the relationship is hypothesized, and estimates of the parameter values are used to develop an estimated regression equation. Various tasks are then employed to determine if the model is satisfactory. If the model is deemed estimated regression equation can be used to predict the value of the dependent variable given values for the independent variables.
Okay, great. And now, can we have a gentleman to read correlation? That means here. Correlation and regression analysis are related.
So for the correlation and regression analysis, are related in the sense that both deal with relationship among variables. The correlation coefficient is a measure of linear association between two variables. Values of the correlation coefficient are always better -1 and +1. A correlation coefficient of +1 indicates that two variables are perfectly related to a positive linear sense. A correlation coefficient of 1 indicates that two variables are perfectly related in a negative linear sense. And a correlation coefficient of 0 indicates that there is no linear relationships between two variables. For simple linear regressions, the sample correlation coefficient is the square root of the coefficient of determination, with the sign of the correlation coefficient being the same as the sign of B1. The coefficient of times 1 in the estimated regressions equation. Neither regression nor correlation analysis can be interpreted as establishing the cause and effect relationship. They can indicate only how or to what extent variables are associated with each other. The correlation coefficient.
Okay. All right, that's good. So this is what I want to tell you, that it cannot give you it can only tell you the strength and the magnitude. So magnitude here, +1, +2. Okay, remember we gave you just now an example that here, with every increment of 1 score, you get increment of 2 mmHg. I will be giving you examples of regression analysis after this. Okay, so this is simply to just highlight the correlation part of it. All right. Okay, let's move on. Here, this is the example of regression analysis that I would like to show you. So this video is about 5 minutes, right? So I hope your connection is all right. If not, just give me give me a shout out. Just tell me in the chat group whether you're able to see this or not. Okay. Otherwise, I'm going to send you the link via the chat group, and you can view it later when your connection is better.
If a new mouse has this weight, then this is the size that we predict from the weight. Although we didn't mention it at the time, using data to predict something falls under the category of machine learning. So plain old linear regression is a form of machine learning. We also talked a Now we are trying to predict size using weight and blood volume. Alternatively, we could say that we are trying to model size using weight and blood volume. Multiple regression did the same things that normal regression did. We calculated R squared, and we calculated the p-value, and we could predict size using weight and blood volume. And this makes multiple regression a slightly fancier machine learning method. We also talked about how we can use discrete measurements like genotype to predict size. If you're not familiar with the term genotype, don't freak out. It's no big deal. Just know that it refers to different types of mice. Lastly, we could compare models. So on the left side, we've got normal regression, using weight to predict size. And we can compare those predictions to the ones we get from multiple regression, where we're using weight and blood volume to predict size. Comparing the simple model to the complicated one tells us if we need to measure weight and blood volume to accurately predict size, or if we can get away with just weight. Now that we remember all the cool things we can do with linear regression, let's talk about logistic regression. Logistic regression is similar to linear regression, except logistic regression predicts whether something is true or false instead of predicting something continuous like size. These mice are obese, and these mice are not. Also, instead of fitting a line to the data, logistic regression fits an S-shaped logistic function. The curve goes from 0 to 1. And that means that the curve tells you the probability that a mouse is obese based on its weight. If we weighed a very heavy mouse, there is a high probability that the new mouse is obese. If we weighed an intermediate mouse, then there is only a 50% chance that the mouse is obese. Lastly, there's only a small probability that a light mouse is obese. Although logistic regression tells the probability that a mouse is obese or not, it's usually used for classification. For example, if the probability a mouse is obese is greater than 50%, then we'll classify it as obese. Otherwise, we'll classify it as not obese. Just like with linear regression, we can make simple models. In this case, we can have obesity predicted by weight, or more complicated models. In this case, obesity is predicted by weight and genotype. In this case, obesity is predicted by weight and genotype and age. And lastly, obesity is predicted by weight, genotype, age, and astrological sign. In other words, just like linear regression, logistic regression can work with continuous data like weight and age, and discrete data like genotype and astrological sign. We can also test to see if each variable is useful for predicting obesity. However, unlike normal regression, we can't easily compare the complicated model to the simple model, and we'll talk more about why in a bit. Instead, we just test to see if a variable's effect on the prediction is significantly different from 0. If not, it means that the variable is not helping the prediction. We use Wald's test to figure this out. We'll talk about that in another StatQuest. In this case, the astrological sign is totes useless. That's statistical jargon for not helping. That means we can save time and space in our study by leaving it out. Logistic regression's ability to provide probability and classify new samples using continuous and discrete measurements makes it a popular machine learning method. One big difference between linear regression and logistic regression is how the line is fit to the data. With linear regression, we fit the line using least squares. In other words, we find a line that minimizes the sum of the squares of these residuals. We also use the residuals to calculate R squared and to compare simple models to complicated models. Logistic regression doesn't have the same concept of a residual, so it can't use least squares and it can't calculate R squared. Instead, it uses something called maximum likelihood. There's a whole stat quest on maximum likelihood, so see that for details, but in a nutshell, you pick a probability, scaled by weight, of observing an obese.
Okay, students, can you hear me now? Okay, great. It's getting a bit technical, so I have switched that off, okay? But what
I want you to tell me what is the difference between correlation and regression. Let's start with variables. Correlation just now, you remember BP versus the stress test score, stress score. Now with regression, how many variables did you see? The rat is obese. What else? You remember there were other factors or variables such as age, excuse me, age, and there was one variable that they had decided to leave it out because it is not important, the astrological sign. You remember there were a few variables there. So what does that tell? Genotype, exactly. So what does this age genotype? Absolutely correct. What does that tell you? For correlation, you can only see the relationship between one variable. So one is always a dependent variable and another is independent variable. Okay? With regression analysis, be it linear or logistic, you can study one or more variables. Okay, the equation, you remember y equals to 49.3 times 0 point something times x. You remember that equation? Okay, it was a very simple equation. In logistic regression, you can have y equals to 49.3 plus the square root of x plus z plus c. Okay, it's a lot more complicated. It means that it can accommodate more than one variable. The other point is, you remember BP and stress score. These are what type of data? Goes back to the first part of the lecture when we talk about type of data. Either you have continuous data, yep. Thanks, Atira. Which means, Nadia, good. It means they are data which can be arranged from a small number to a large number. All right. In logistic regression, the example just now, it is whether a mouse is obese or not. Okay. And the weight is, of course, the continuous data. But remember, I did tell you that you can transform continuous data into categorical. You remember the example of the height, where we put 160 cm to 170 cm into category 1, then 170 cm to 180 cm into category 2. So here they have done similarly. They have used the weight of the mouse categorize it into different categories. So 1, 2, 3 with increasing weight. Okay, and the other point is age, you had genotype, okay. These are all variables which are categorical in nature, okay. Correlation is more for continuous data. Regression analysis, for example, logistic regression is for categorical data. Can you tell me what type of categorical data, the two subtypes of categorical data? One is using based on location. Oh, no. That is actually descriptive data. Yes, nominal or ordinal. Arina, good. Irunisa, yeah. Ordinal is one, the other is nominal. Yes, that's good, Fatin. Okay. So, yes, good job, everybody. Nominal and ordinal. Okay, so you have to give it a name or you have to put them in order. Rank is not accurate. Rank is not, well, another word for ordinal, you can say it can be ranked. Okay, it's a description of ordinal data. Okay, it's not actually a subcategory. It's a way of describing your ordinal data. It's by ranking in order of the disease severity. Okay, for example. All right. Now, I hope you have an understanding of what they are. All right. So I am going to more sort of technical because I believe you have understood the principles behind the importance of knowing whether your data is normal, not normal, because normal data, you're going to use parametric tests. Non-normal data, you're going to use non-parametric tests. Okay, I know I've used these terms many times, parametric, non-parametric. I will end this presentation with a list of names of the parametric data, non-parametric data. Okay, but at this point in your studies, it is not absolutely necessary for you to know all the statistical tests that you can use, but you should know the principles. Okay, so therefore, abnormal or normal data, you have to know why they are normal or abnormal so that you know normal, parametric, non-normal, non-parametric data. Okay, and then so data summarization. Okay, so you can have thousands. In fact, some clinical trials have millions of a sample consisting of millions of patients because perhaps you want to give a conclusion for the billions, okay, of people in the world. Okay, so you're using a sample of 1 million patients to give a conclusion for the billions that live in other countries as well. Okay, so data summarization using techniques such as graphical illustration or descriptive statistics or even inferential statistics, okay, to help summarize your data. Otherwise, can you imagine 1 million subjects, okay, so n equals to 1, n equals to 2, n equals to 3, until you have reached 1 million, and how are you going to summarize that vast amount of data, okay? So basically, data summarization is the process of describing a data metric by computing a small number of measures that characterize the data set. Okay? When we say small number of measures, what we mean is we're extracting measures such as age, genotype, weight. Okay, these are measures. Okay, but effectively they characterize your entire data set. You summarize your vast amount of data, you get more understanding, okay, applies understandable conceptualization, communicate underlying patterns. Okay, you want to see patterns. Okay, remember we wanted to see whether the rat with increasing weight, is it obese or not? Okay, but of course that is a very simple simplification because as we know, obesity is so closely related to weight, right? Okay, but what they were saying earlier is it's not just weight, you also have genotype. Okay, your gene composition also affects your whether you're obese or not. And then here, lastly, when you use inferential statistics, you can generalize your sample findings to the larger population. Here is just to give you a graph which I described earlier. Okay, are you able to see the graph? Normal distribution graph. Okay, great. Thank you, Daniel. In a normal distribution, mean and median are the same. Thanks, Adila. Here, this red line represents mean or median. So when your data is normally distributed, like in this case, it gives you a bell shape. You can also call it symmetrical graph. Here, your mean and the median, if you were to calculate, will be the same. When your mean is not the same as your median, then it means it is not normally distributed. We'll see an example in the next slide. Here, you remember a few terms that we use. Just now, one of you said location, spread of the data, central tendency. Okay, these are all ways to describe your data. So you see here standard deviation. Okay, is the extent of the spread of your data around the mean. Okay, how close are all your other data towards the mean? How close are they? Okay, so this is standard deviation. Okay, here cases distributed symmetrically the mean. Okay, so this shows you how a normal distributed data would look like. Here, this is skewed distribution, skewed to the right. So here, if you were to plot, your mean would be here, your median is here. Again, this goes back to the principle of why you need to know whether your data is normal or non-normal, because here it is very obvious it is not normal, it's skewed to the right, and therefore you have to use median to report. Okay, you cannot say, oh, the mean of my data is blah, blah. You have to say the median of my data because my data is not normally distributed. Okay, so median is actually means 50% of the values will lie on either side. So here 50%, here 50%. Okay, so normal graph, you will take the middle point here. Okay, but you can't do with non-normal data. Okay. Okay, here, this is the complicated part, but it puts together all that you have learned. You remember continuous data, categorical data. Remember, I told you it's important to know one group, two groups, how many groups, paired or unpaired. Why is it important to know whether your data is paired or unpaired? Can you give me an example when you say your data is paired? Paired means, okay, when we take a single observation of all of you, does that mean that your data is paired means there is a repetition. Okay, so remember paired also means dependent on each other. So your first observation is dependent on your next observation. So these are paired data. Okay, now it puts together everything, continuous, categorical. You remember you have to know whether your data is paired or unpaired. So here, when it says one group means they only took one observation. Remember, we wanted 10 of you to just jump as high as you can, and we just want to measure how high you can jump. That is one group, only one observation. Okay? So when you have only one group and your data is continuous, such as BP, height, or weight. Okay, variables such as BP, height, or weight, which is continuous, you use one sample t-test to calculate the significance. Okay, for statistics, you will use one sample t-test. Okay, And here, as I said, this slide put together everything: normal, non-normal, skewed. Okay, skewed also means not normal. Okay, so not normal always uses non-parametric tests. So these are all your non-parametric tests. Okay, normal data will use parametric tests, and these ones in red are all your normal parametric tests. Okay, and then categorical data, okay, will use regression. Okay, such as this. All right. So I believe that is the last slide. I just wanted to say a few things. Let me switch on my mic, my video now. Okay, are you able to see me? Yes? Okay. All right.